So, whenever I make any kind of assumption, I'm usually wrong. Over here we've got Desmos. I assume most math students nowadays know about it. Nice, friendly, online graphing tool. We happen to have a Mac, a similar program called Grapher. Does nice stuff with 3D if you need 3D. And these are useful tools when you're graphing, or sometimes when you're doing homework, if you want to check that something makes sense and really how does an equation. Sometimes you put up a graph and it helps out. Thought I'd start today by graphing this kind of curious looking creature x raised to the x, which unsurprisingly, as you go off to the right, becomes, just goes wildly up. It's interesting, it has a minimum, but really, for today, the reason I'm putting this up has to do with its behavior as we get close to 0. I write that as the limit x approaches 0 of x to the x. Now, without looking at this nice rendition here, you might kind of scratch your head. Where's that going? 0 to 0, what's that even anyway? It's undefined. It'd be nice to think it's 0, but almost everything to the 0 is 1. So, kind of a little mystery. Graphing it kind of helps. At least it looks like it's going to 1. But we would like a more analytical way to investigate this and other things that are kind of mysterious. Kudos to Desmos for pointing out that there's kind of the discrete points out here you can draw in the real world. You might think, well, what's that about? Well, -1 to the -1. That's would be -1. I guess that's over here. You might wonder, well, how can this be just, a nice continuous looking function that's not smooth, but then again, what's -1 to the -0.34? And the answer is the complex plane. But we're not doing that. We don't do that in this class very much. We're not that interested in complex numbers. So, okay, so I'm going to put this away. I just thought we'd start with a little visual view of things. I guess I'm going to turn this off for now, but it may come back. So, the topic we're going to cover is called L'Hopital's rule. Spelled, I guess there's a dispute about this. Our book says it should be spelled this way, which I guess the French pronounce it L'Hopital. Or does it have an O with a little hat on it? I kind of like this better because I'm not as inclined to mispronounce it. But L'Hopital was a nobleman in France, apparently wealthy, and he did not come up with L'Hopital's rule. You may have heard this story before. L'Hopital's rule was invented by one of the Bernoulli family. Bernoulli's had a large number of very influential mathematicians and scientists in the 1700s. This is it's credited to either Johann or John, or even that. The math books aren't very clear. Probably you need a history of math course to get that worked out. And we're also going to look at something called an indeterminate form, which is crucial to L'Hopital's rule. This is all section 4.4 in the book. So you might as well start off by writing L'Hopital's rule. If a limit f of x goes to an indeterminate form, well, let's do it this way. Indeterminate form. We'll just use x going to 0 for right now. You can expand this to other values. No, we can just say a, all right? For now, think of indeterminate form as f of a equals 0, f of g of a equals 0. If that's the case, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of derivative of f of x over the derivative of g of x. Okay. Let's take an example that we're already familiar with. Someone remind me the limit as x approaches 0 of sine of x over x. You would recall we looked at this when we were looking at the derivative of the sine and the cosine. Can you recall the value? Okay, this is a good one to know. We did a kind of geometric proof demonstration that this is 1. But using L'Hopital's rule, let's see how we would evaluate this. Well, as x goes to 0, sine of x, sine f of x goes to 0. Sine of 0 is 0. And of course, x goes to 0. So it's not clear what this, off the top, what this should do. It depends on when we're getting very close to 0, what happens. But since it's an indeterminate form, we apply L'Hopital's rule. Derivative of sine of x. Derivative of x is the limit. Derivative of the sine, everyone knows, is the sine of x, and derivative of x equals 1. And here, since cosine is a continuous function, we know the cosine of 0 is 1, so this just equals 1. That's just a very simple example of what we can do with L'Hopital's rule. Looks so far. Now something like this, sometimes it's just some obvious as a picture you can look at and go, oh yeah, of course, that's going to be the case. Or sometimes there's a straightforward algebraic way to show it. I always thought this was like some mysterious kind of thing that we wouldn't do in a class at this level. It turns out that's not the case. It's actually pretty straightforward. Let's go ahead and, at least for the simple case of x going to 0 and the indeterminate form 0 over 0, this is a simple demonstration. We won't do the whole general L'Hopital rule, but I think it's just worth seeing that it's not that far, it's not that strange. Okay. So we assume we have two functions, f of x and g of x, that are continuous, and that for some a, f of a equals f of b equals 0. And furthermore, we, my brain and my hand are not working right. F of a and g of a is 0. And also, g prime of a is not 0. It's not going to do us any good if we end up with a new limit that we also can't evaluate. Okay, so we're going to go back to the definition of a limit. Well, let me write it all out. I'm definitely off today. What we're going to do is we're going to evaluate this construction. The limit as x approaches a of the derivative of x over the derivative of g. No, actually, I don't think we need a limit here. We just want to look at this. Okay, so this is the limit, the definition of the limit. This is the limit as x approaches a of f of x minus f of a over x minus a. Now, you might recall when we first looked at the definition, we used a slightly different version that was equivalent. We used limit x approach as h approaches 0 of f of x plus h minus f of x over h. If you examine these, they're completely equivalent, right? As x minus a, as x goes to a, x minus a, of course, goes to 0. So we're just using h in its place. And as f of x plus h goes to 0, that just becomes f of x. Okay, so going back to this construction, we have the limit as x approaches a of g of x minus g of a over x minus a. That's again, definition of a limit for definition of the derivative of g of x. Right. Well, using the limit rules, it's just the limit as x approaches a of f of x minus f of a, or x minus a g of x minus g of a over x minus a. But for everywhere except at a, we can remove this. And since we're interested in the limit, it's fine. So this is just the limit of x approaches a, f of x minus f of a over g of x minus g of a. And the final step is to remember our assumption that f of a and g of a is 0. So the limit as we go to f of a and g of a is just 0. So this is just the limit as x approaches a of f of x over g of x. So if you look at where we started, I guess I did need this limit here, didn't I? This is the limit as x approaches a of derivative of f of x over the derivative of g of x. Okay, that wasn't, there's nothing, no real fancy math there, just using the limit law and some algebra. Now this again is not a complete, this isn't a complete proof of L'Hopital's rule. L'Hopital you can have either limit at a constant, you can have a limit at either negative infinity or positive infinity. The indeterminate forms can be 0 over 0. They could also be infinity over infinity. That is, if you have two functions and they're both getting very, very large, we can apply L'Hopital's rule, infinitely large. Negative infinity is also, over infinity is also possible. There are a few more indeterminate forms we will look at, which are, there's more involved to apply L'Hopital's rule, but they still correspond. I need my list. Where my list is, so I'll just make it up here. We go to 0 to 0, from 0 to 0, infinity to 0, 0 raised to the power of infinity, and 1 raised to the power of infinity. Now, these are not numbers. These are just kind of a template or a form. If we have some function that ends up looking like this at its limit, then we know we can apply L'Hopital's rule. Now, let's just do an example first. Running out of workspace here. We want to know the limit as x goes to 1 of the natural log of x over x minus 1. So step 1 is always verify that this is an indeterminate form. The log of 1 is 0. 1 minus 1 is 0. So this is going to 0 over 0. So we can use L'Hopital's rule. All right. L'Hopital's rule says this is the limit as x goes to 1 of derivative of the log of x. We should all be conversant with that. 1 derivative of 1 over x, thank you. Derivative of x minus 1. You should do that in your sleep. Derivative of x minus 1. 1. Okay, so now we want the limit of 1 over x over 1, which is obviously going to be 1 over x, but if x goes to 1, this just goes to 1. I feel like a visual on that might be a good thing.
Yeah.
Okay, so we're interested in 1. Okay, so I don't know if you can see this up here. Can you see where it says 1 undefined? Right? But if I move it off a little, 1.02, 0.99, this direction 0.98, 101, right? So this is just another way you can confirm what we're doing here. Right? Another example. Let's take a look at a limit at infinity. The limit as x goes to infinity of x squared minus 1 over 2x squared plus 1. Now, at the risk of sounding tedious and boring, I'm going to repeat. The first step is to make sure this limit goes to an indeterminate form. We see as x goes to infinity, x squared certainly goes to infinity. As x goes to infinity, 2x squared plus 1 certainly goes to infinity. So this is going to infinity over infinity, an indeterminate form, so we may use L'Hopital's rule. We're going to get limit as x approaches infinity of, okay, the derivative of x squared minus 1 is
2x.
2x, thank you. Derivative of 2x squared plus 1 is
4.
4x. Okay, now, you actually could apply L'Hopital's rule again, but let's just realize this is the limit as x approaches infinity of 2 over 4 times the limit as x approaches infinity of x over x, which clearly goes to 1. This is a half, so this is just a half. It might be worth noting that this is not necessarily the best way to solve this. There's an alternative. You could take this original expression, divide the top and bottom by x squared, and you get 1 over x squared. I'm sorry, you get 1 minus 1 over x squared over 2 minus 1 over x squared. And, you know, as x goes to infinity, clearly 1 over x squared goes to 0, and you can just immediately jump. That's not true for all the problems we're doing. Some of them you would be, you won't find an easier way. Now, here is an example of something. Limit as x goes to 0 of x plus 5 over 2x plus 5. This is not an example of when to use the L'Hopital's rule. Because I look at my first step, and I say, oh, well, it goes to 5 over 5. That's not an indeterminate form, and it would be inappropriate. We can see right away, this is just going 1. But let's see what happens when we misapply the rule here. Well, derivative of x plus 5 is 1. Derivative of 2x plus 5 is 2 half. And I'm trying to avoid the disaster of applying L'Hopital's rule when we don't have an indeterminate form. It does not work. Okay. We're going to take a look at some more interesting problems. We can use this new tool. Limit as x approaches infinity of e to the x over 2x. Okay. You've been around the math circuit a while. You have an instinctive kind of feel for this, which I'll mention afterwards. But clearly e to the x, that's going to infinity. X as x approaches infinity. 2x is also going to infinity, so we can apply the rule. All right. Derivative of e to the x is e to the x. Derivative of 2x is 2. Ah. Well, clearly, now we just have an expression that's going to infinity. The point I wanted to make earlier is exponentials grow much faster than any polynomial. If I give you an exponential point, as long as it's bigger than 1. And I want to compare that with 5 million x to the 50,000, you might think plugging in x's, you're going to get a larger number here. You will for a long, long time. But at some point, out in the far reaches of the number line, this will exceed the polynomial. It just always works that way. Oh, you know, I should have my list. Here's some more indeterminate forms. 0 times infinity. Infinity minus infinity. I think I wrote this one. Infinity to the 0, 0 to the infinity, 1 to infinity, 0 to the 0. We looked at 0 over 0 and infinity over infinity already. See if we can get a few more exact examples. All right. Let's look at the limit as x approaches 0, but from the right. Powell's rule works for one-sided limits as well as regular limits. Okay, so what do we have here? As x goes to 0 from the right, this is going to 0. And what happens as x goes to 0 to log of x? So we're getting teeny tiny numbers. We're finding the log of them. If I were to graph e to the x, I think that's pretty obvious. It goes to 0. It's very large. And it comes down this way, asymptotic to the x-axis, right? Put in like -5. It's like 1 over e to the 5, right? So it's a very small number. So it's inverse natural log of x. It'll look like this. And now you can see why we want to come at this to the right. What happens here? Is it approaching?
Negative infinity?
Absolutely. Okay, so I didn't actually list 0 times negative infinity, but it anyway. So this is an indeterminate form that we can apply L'Hopital's rule to. However, it's not real obvious, right? We don't have the division here, do we? So we have to be a little creative. How can we make this? Well, we rewrite this as log of x over 1 over x. kind of a sleight of hand there. Now the form we're going to is not 0 times negative infinity, it's negative infinity over infinity. So we can apply L'Hopital's rule. Okay, the derivative of the natural log of x. I think did we already see that today? Yeah. Just 1 over x. And x to the minus 1 is just minus 1 over x squared. Using our limit rules, you can see that this is what? This is just log of x approaching 0 from the right, negative x. Which of course goes to 0. I'd like to see that. I really would. And, go. Now, you know, you can learn a little more here again. As a minimum, that function is a good thing, but comes in from the negative side and gets to 0, or it approaches 0. Right. That's what we have here. You know, I encourage you when you're doing the homework, you know, it kind of adds a bigger view of, so to speak, no pun intended, of what's going on. Why do these things go where they go? Well, as they get small, something's happening. You can see that. Okay. So this next is kind of like a magician. I'm just kind of pulling rabbits out of a hat here. The next trick, limit as x approaches 1 from the right of 1 over log of x minus 1 over x minus 1. Okay, first step, see if there's an indeterminate form. Well, as we get to 1, the log of x goes to 0. 1 over 0 is infinity. And as we subtract 1 over x minus 1, well, clearly this is going to 0, so it's infinity minus infinity. Clearly, think about that term indeterminate. It's like it's not obvious what's going to happen. It could go to infinity, it could go to negative infinity, it could go to 0. It depends on what happens to these functions as you get close to 1. All right. So again, you know, we're going to have to use, you know, to apply L'Hopital's rule, we're going to have to use a little creative algebra here, but it's not all that obvious. Let's put these over a common denominator. So obviously the common denominator is going to be log of x over x minus 1. So I have x minus 1 minus the log of x. So this goes to 1. X minus 1 goes to 0 minus 0. So you're going to have 0 over, well, this is going to go to 0. And this is going to go to 0. So we're still in indeterminate form. Now we can apply the rule. So we did this. That's 1 minus derivative of the log over x. Okay. I could use the product rule, but I think I'm just going to, I'm going to have to use the product rule anyway. All right, so log of x times the derivative of x minus 1, that's 1, plus x minus 1 times the log of x. I mean the derivative of the log of x, 1 over x. All right, let's see, are we getting closer now? 1 minus, oh, that goes to 0. And we've got 0 plus 0 over 1 to 0. Any thoughts on this? We're kind of back where we started. We still have an indeterminate form here. We can't just plug in 1 and figure this out. Maybe we have to use L'Hopital's rule again. Maybe that would be helpful. All right. Can we simplify this at any? Well, let's multiply the top and bottom by x. So we have x minus 1, x log of x, plus x minus 1. Clearly again, we've got it. Now we have 0 over 0 again, of course. Let's find the derivatives. Derivative of x minus 1 is 1. Derivative of x times the log of x. Again, product rule. X times 1 over x plus log of x. That's this. Really comfortable with that? I ran through that. X times the derivative of the log of x plus log of x times the derivative of x. X times 1 over x plus log of x plus the derivative of x minus 1, which is 1. Okay, so what do we have here? 1 over x plus log of x plus 1. What happens when that goes to 1? Top obviously goes to 1, this goes to 1, this goes to 1, 2, and this goes to 0. There it is, it's a half. Who would have thought? We did this. All right. I don't like this idea here. Let's take a look at this function. Now, we've gone to 1. Can everyone see that? Again, undefined, but it's pretty clear if you look at the scale, it's 1/2. We're awful at all we can see. 503, 98. I think we're going to take a break now, a few minutes early. Stretch, come ask me questions. So, I may be repeating myself. For the next midterm and the final, it will be acceptable to bring along a sheet of paper. I think the common name is cheat sheet. You can write things like, get rid of the art sign, because that's not something easy to remember. Right? The product rule. You can write the phone number of someone you want to call. You won't be able to, but you can look at it. Okay. Try. Whatever you want. I haven't come to an answer yet, but clearly I don't mind if you use a calculator to calculate numbers. Ordinarily, I wouldn't be concerned about you having a graphing calculator, because I don't think that's a bad thing to be able to graph something if you want to look at it. My concern is fairness, that not everyone has a graphing calculator. Is that a fair statement for people who don't have graphing calculators? I don't know if that's feedback or not. Does that mean everyone has a graphing calculator? Some people do. I'm worried about the people who don't. Okay. Maybe what we'll do, maybe what we could do if people would like to use them is bring in some Post-its, so you can put your name on it, and then when you're not using it, you can clear it. Somebody else can use it. Is that, I don't know if that's legal. Does that violate the rules of COVID? Well, okay, think about that. I'll talk to the people at the school. Again, I think it's, in the recent past, those calculators were just part of the course and everyone had to have one, and I know they're moving away. Maybe use Desmos from a laptop would be nice, except that that's not going to work on an exam. So, and I guess we could write, yes?
For the cheat sheet, do we get like a full-on sheet of paper or like an index card?
It's a reasonable question. If I gave everybody just an index card and said, you can only write on one side of the index card, there's somebody in this room with really good handwriting who's going to, write in like 0.5 point type. So, no, you can have a full sheet. You can write on the back. Okay.
Anything you want?
I'm gonna be very disappointed if somebody like finds a way to like microfiche the entire book onto a sheet of paper and brings along a microscope to look at it, but there's a diminishing returns with that, you see. The more stuff you have on your sheet, the more you have to kind of look through it, unless you know exactly where everything is. And if you know where everything is, you probably know it already, you don't need the sheet, so. All right. No sharing of sheets, sorry. Although I guess if your friend did a nice one, you can Xerox it in your own copy. And if you can't double-side print it, you take two sheets and staple them together, that's okay too. What else did anyone ask? Okay, I wanted to say that there's a problem. Does anyone have the book? Nobody has the book. There's a problem I was really interested in, but it hasn't been corrected yet. I think it was number 36 on the linear approximation. Anyone remember that one? All I remember is it had, maybe you haven't turned it in yet, cosine at 29 degrees. Anyone remember that problem? Yeah, I guess I want to see what happens with the greater hand side. There's a little story related to this. Okay. All right. I know where I wanted to start. This may sound like not a digression. This is like a non sequitur. But does anyone remember when we were looking at like this function and we wanted to find its derivative? Does anyone remember how we should remember how we do this? Anyone recall the name of what we do? Well, so it's worth going over, isn't it? This will dovetail into what we're doing in a minute or two. So it's called logarithmic. Bad spelling. Logarithmic differentiation. So we just treat this as this function as an equation. And we find the natural log of both sides. And we use our knowledge of logs of this exponent over here. And now we're doing what? We're doing implicit differentiation. Differentiate both sides. So the derivative of the log of y is 1 over y times y prime. And we just did this earlier today. So it's x times 1 over x plus log of x times 1. 1 plus log of x. So our derivative, y prime, is we can multiply through by y plus log of x. And of course we know what y is, it's x to the x. So we find that the derivative of x to the x is x to the x times 1 plus log of the x. Okay. through that again because I got a blank stare. Before the midterm, I go back and look at procedure. But there's kind of like a moral lesson here in math. Is if you have an exponent that is causing you problems, maybe take the log, and because when you take the log, turn an exponentiation into a multiplication. Sometimes that's easier to handle. All right. So, what the heck does that have to do with what we're doing? So we want to look at limit as x goes to 0, 1 over x to the x. So my first step is to, just want to see if people forget everything after the break. My first step is to, thank you. 1 over x is going to infinity, and x is going to 0. Here we have one of my forms. So good. We can do this. But I'm not really sure how to do it. All those other problems, I could turn this into a fraction. I mean, I could do this. I could do 1 to the x to the x, so that's 1 over x to the x. That doesn't really help, does it? Doesn't really do anything for me. I mean, this goes to 1. I don't know where this goes yet. Actually, we do know, but it doesn't matter. It's not an indeterminate form. So that's not important. So instead, we say, all right, let's let this be y. And let's try that trick. Let's find the natural log of both sides. The log of y, well, the log is going to come inside the limit. But of course, x log x. And we've seen this before, something like this, where you have a product and you just rewrite it. Okay. Well, we better check again and see if we're on the right track. X goes to 0, 1 over x goes to infinity. Log of 1 over x. Well, as 1 over x goes to 0, this goes to infinity. And the log goes to infinity. So we're good. We can apply L'Hopital's rule. Right? Derivative of the log of 1 over x. I need to rewrite that. That's going to be 1 over x times the derivative of 1 over x. Well, that's going to be negative 1 over x squared. And down here we have, again, this is x minus 1 over x squared. Minus 1 over x squared. Let's multiply by x squared. So we're going to get x cubed minus 1 over, well, we've got a minus sign in there still. And that was our limit as x went to 0. Well, what happens when this goes to 0? Got a negative here, a negative here. This goes to 0. This should equal 1. Keep in mind, we're not done yet. What we've shown is that the log of y is going to 1. So if the log is 1, what's y going to? Well, when you have a log and you want to get rid of it, raise it to the e to that power, right? So y should be going to e. Let's test our idea here.
So it equals to 1. Right? The whole thing equals to 1. That's my goal. I'm gonna try my own.
You know, I did something wrong. Didn't I? Well, let's discover that the graphic way, and we'll go fix it.
Yeah.
The boo-boo here. Well, something's amiss. This is telling me 1. Anybody catch me at what I did? I did wrong. Let's see here. Oh, yeah. Yeah, I think I wasted a lot of effort here. I know where the mistake is, but let me go back. Yeah. Well, not sure why this didn't come out the way I was hoping, but obviously I made some kind of error there. So this goes to infinity, this goes to infinity, this goes to infinity. But I can rewrite this as negative log of x, 1 over x. All right, so now when I find the derivative, what do I get? On top I do have negative 1 over x, on the bottom I have negative 1 over x squared. This just becomes x, so it goes to 0. So that's my y. I'm sorry, that's my log of y. So if log of y goes to 0, y just goes to 1. I'll take a look at the tape. See what I did wrong. All right, so these, you know, you got to be careful with your math here. I have to be more careful. All right. Yes?
So the x goes to 0, and then how does the y equal to 1 again?
Oh. Okay, I start with this, right? But I find the log of both sides. I mean, y is what I'm looking for.
Yeah, I understand. So, like, you differentiate the both sides, like the top and the bottom. You differentiate both.
I apologize, I just cannot make out what you're saying, but
So you differentiated the top, and then you differentiated the bottom. And then how the x goes to 0.
From
then.
here?
Uh-huh.
well, as I was trying to get to, log of y equals 0.
Oh, okay, thank you.
So if I raise both of these to e to the log of y, they're inverses, I just get y, and e to the 0 is 1. Yeah, I jumped there.
Thank you.
That's like, stop me when we run into these, but you need to know your laws of logs, you need exponentials and trigonometric functions, all those come in what we're doing. Okay. I guess it makes me a little long-winded, but I'm trying to give you one of each of these examples here. So let's take a look at. Stick my y in right away because I know what's coming. Y is the limit as x approaches 1 of x to the 1 over 1 minus x. Okay, so what is this going to? X is clearly going to 1. And this is going to 1 over 0. It's going to infinity. So this is going to 1 over 10. As with the previous example, we look and we see, we've got an exponent that's kind of hard to deal with. Let's find the log of both sides. Okay, that lets us move the exponent over. Right. Now let's take a look at this. As x goes to 1, the log goes to 0. And 1 minus x goes to 0. Cha-chung. We can use the rule. Derivative of the log is 1 over x. Derivative of 1 minus x is minus 1. This just becomes minus 1 over x. And as x goes to 1, this should go to minus 1. That doesn't sound right. Doesn't sound right at all. Oh. Yeah, it doesn't sound right because I didn't finish. Y is going to minus 1. I'm sorry, y is not going to minus 1. The log of y is going to minus 1. So, All right. Let's take a look. Raised to 1 divided by 1 minus 6. And we were looking as the 1. That's kind of over here. E is about a little less than 3. So this point should be a little more than 1/3. See what this most comes up with. Yeah, a little more than 1/3. Well, I guess undefined, of course, that point. This could be a topic further research again. When you have negative exponents in the real world, there's just kind of discrete points. But, let's take a look now at, this shouldn't come as a surprise. The limit as x approaches 0 of x to the x. So we're looking at what? X goes to 0, x goes to 0. So we're looking at the form 0 to 0. Well, clearly we're going to use the same strategy. Log of y equals the limit x approaches 0, the log of x to the x. It's just going to be x log of x. Or, no doubt, we're going to write it as log of x over 1 over x. And again, log of x goes to infinity, or negative infinity, as we get close to 0, and 1 over x is going to infinity. So we can apply the rule. So derivative of the log of x is 1 over x, and derivative of 1 over x is negative 1 over x squared. Any psychology or neurology people in here? I keep doing this thing, like I was going to write x squared, but my hand wrote a 2. You know, like, some little neurological thing where my hand is ahead of me. Okay, I'll start. Limit x approaches 0 of, it's going to be negative x, of course it's going to be 0. But once again, that's the log of y equals 0, so y should be equal to 1. Our limit is 1. I'm not going to cover this. If you think about the example here where we went to infinity to the 0, let me pull that up again. Yeah, it was limit as x approaches 0 of 1 over x dx. Well, if you just rewrite this, rewrite it as x goes to infinity, x to 1 over x, it's the same problem, it just comes out different form, but it's not that different. So I don't want to do that. I don't want to do that one. I do, however, want to show you the benefit of persistence. That is, being a persistent person. Fine line between persistent and pushy. Persistent is like when you're on your own doing something. Like pushy is like trying to get somebody else to do something. All right. Persistence has its advantages in certain fields like computer science, and disadvantages in, I don't know, HR departments. Okay. Let's look at the limit as x goes to 0 of tangent x minus x over x cubed now. Once again, you're going to be implored to strengthen up your trig if it's a little weak, especially when it comes to derivatives. Tangent of 0 is sine over cosine. Sine of 0 is 0. Tangent of 0 is 0. Minus x minus 0 over 0. So this is going to 0 over 0. Two zeros. There, I did it again. Okay, so we can apply the rule. Derivative of the tangent of x. I guess that's going to go on the cheat sheet, isn't it? Right. Secant squared x minus 1 over 3x squared. I'm going to leave off the limits, you just can mentally put them in. So the secant is 1 over the cosine. The cosine of 0 is 1. So this is going to 1. 1 minus 1. Still going to 0. This is still going to 0. So I can apply the rule again. Okay, derivative of the secant squared. Well, now we have to use the chain rule. 2 secant of x times the derivative of the secant of x. Again, cheat sheet material, right? Secant x tangent of x. Look at my cheat sheet. Find it. Oh, because I wrote it wrong. Too bad. Well, the 1 goes away. 6x. Okay, let's check again. As we go to 0, secant goes to 1, secant goes to 1, tangent goes to 0, 6x goes to 0. How many times have we applied the rule now? Twice? We're going to do it one more time, right? Well, we might want to see if there's something we can do here first. So 2 over 6, so we get a little simplification. Secant squared x tangent x over x. Well, we know what the secant squared is going to. It's going to 1. So maybe what we want to do is rewrite this as the limit as x approaches 0 of secant squared x times the limit goes to 0 of tangent of x over x. Because this is just 1. That helps. Okay, so now we're down to the limit as x approaches 0, the tangent of x over x. Tangent goes to 0, x goes to 0. We can apply the rule. Rid of the tangent is secant squared of x over 1. And the secant squared is going to 1. So this all becomes 1. Up. Yeah, the only problem is I guess, I guess I got the wrong answer. That's because I forgot to put in a long line 1/3. There we go. No one copied that. There we go. I gotta see this. Let's see if after all that we're in the right spot. Cubed. Let's multiply. X cubed. Okay. We are. Zero undefined, but look how close we are. Right there, a third, a little off. All right. L'Hopital's rule, really nice way to find a limit if it's not obvious otherwise. First thing you always check is an indeterminate form. If it's not, you can't use it. And a little practice on homework and you'll be experts. I think we're done for today. Thank you.